This is part 7 of the series Calculus Prerequisites, and we're continuing on with the review of exponent properties, and we're going to work on this problem next. So here we have m times m squared times n to the 5/3 all to the second power. I'm going to work inside the parentheses first. Here we have m to the first times m to the -2. So we add the exponents. So that's m to the -1. So this is m to the -1. And that's n to the 5/3. And that's all squared. Now that squared term goes to each one of these. So -1 times 2 is m to the -2. And multiply this by 2. It's n to the 10/3. And so now that's all we have to do is straighten out this exponential, this negative exponent here. So we have n to the 10/3 over m squared. Now let's go down to this last problem. The only thing we really have to be concerned about is that we don't make any silly mistakes and mess something up. So let's look at commonalities. We have 3 terms that have a y in them and 1 term that has an x. So this isn't going to simplify with anything other than perhaps numbers. And there's nothing with a factor of 2 or factors of 4 here. So this guy's pretty much going to remain the same throughout the whole process. But we do have a 3 here and a 3 here, so those can go away. So let's rewrite this now. We have y to the 1/4 over 4x to the 3/2 y to the 3/2 y to the 1/2. Now I'm just going to look at the denominator here first. So let's rewrite the numerator, y to the 1/4 over, and this is going to be 4x to the 3/2. Now when we have the same base and we're multiplying, we add. So 3/2 plus 1/2 is 4/2, which is just 2. So this is y squared. Now we look at this and we have y to the 1/4 over y squared. If we convert this to fourths, that's the same as saying 8/4. So we have 1/4 minus 8/4 is -7/4. So this is y to the -7/4 over 4x to the 3/2. And the final piece of this, we just have to take that negative exponent, and that goes in the denominator. If it was in the denominator, that negative exponent would come up as a positive in the numerator. So this becomes 1 over, rewrite that first term, 4x to the 3/2 times y to the 7/4. And that's it. All right, next thing we're going to look at is exponential equations. Now, there are several ways to solve exponential equations. One is using logarithms, and the other is without using logarithms. I would like to solve these exponentials without using logarithms because we haven't yet reviewed any of the logarithmic properties as of this point. But it's fairly simple to do. The trick is, there's no real trick, but the idea is to get both sides to a common base. And the reason for that is because we want to use the one-to-one property of exponentials. If you recall the graph of an exponential, it looks something like this. It's a one-to-one function, which means for every x, there's a unique y value. And so what we can do then is we can eliminate the bases once the basis is the same and have the exact same expression. So see if we can convert 125 to an exponential with a base of 5. And as it turns out, that's 5 to the 3rd. So this is 5 to the 3n equals 5 to the 3rd. Now we can go ahead and use the one-to-one property of exponentials, and this simply becomes the exponents are equal to each other. 3n equals 3, n equals 1. Well, this problem is pretty straightforward because it's already given us in the same base. So the exponents are equal due to the one-to-one property. So negative 3x equals x minus 1. That's just a simple algebra. So 0 equals 4x minus 1. 1 equals 4x. 1/4 equals x. All right, let's move up to this one. Can we put this 81 in terms of an exponential with a base of 3? Well, yes, we can. 81 is 3 to the 4th. So this is 3 to the negative 2k equals 3 to the 4th. So using the one-to-one property, negative 2k equals 4. And if we divide by negative 2, k equals negative 2. All right, now the last one here. We are going to have to try to convert this into some exponential with a common base. These two have bases of 4, but this one doesn't. This one has a base of 2. This one can be resolved down to a base of 2, and so can this. So that's what we're going to do first. Let's start off over here. 1/8 is simply 2 to the negative 3. So this is going to be 2 to the negative 3 to the 3x power. Then 64 is 2 to the 6th. So that's 2 to the 6th times, or to the 2x plus 1 power equals, and this one is 2 squared. So now we have everything in terms of the same base. Now we just have to resolve these exponents here, and we multiply. Because we're raising to a power, we come down 1 in order of precedence, so it's power to multiplication. So that's negative 3 times 3 is negative 9, 2 to the negative 9x. This is 2 to the 12x plus 6, and this is simply 2. So we have the base is the same for all these terms. Now we have to combine this. So we have two exponentials with a common base. We're multiplying, so we add. And so that gives us 2. 12 minus 9 is 3. X plus 6 equals 2 squared. Now we can use the one-to-one property. 3x plus 6 equals 2. That gives us, let's go up to the top here, and we'll subtract 6, so 3x equals negative 4, x equals negative 4/3. All right, so now let's move on to properties of logarithms. And as you remember, logarithms are the inverse of exponentials, so they're going to be related here. And here I presented a quick recap of the basic logarithmic properties using the natural log. And you know that ln of 1 is 0, and the reason for that, of course, is because if you look at the graph of natural log, it looks something like this, and ln of 1 here is 0. And that's not the reason natural log of 1 is 0. We're going to look at the definitions of natural log when we get into our calculus discussions. The definition of natural log is based on a calculus definition. But here we have the natural log of a product is the sum of the natural logs. And this is the power rule. So this is the product rule, power rule, quotient rule. Hopefully you remember those. This is the basic common base law, where you have log to the base a of a to the n is n. Notice the base of the exponential here is the same as the base of the logarithm. When the bases are the same, they cancel each other out and you just have the exponent left. And the natural log of e to the n, because ln, remember that ln is the same as log to the base e. So this is just a restatement of this law, because what you have is log to the base e of e to the n. And these guys cancel out and you still have the n. So that's what this law is about. This is the change of base rule. Log to the base a of b equals log to the base c, some different base of b, over log to the same base of a. Now characteristically, when we have these, let's say that we have some expression that's log to the base 8 of 6. Generally what we'll do with change of base is use natural log because it's a key on our calculator and it's more convenient. So this would be ln of 6 over ln of 8. So that's a standard way to use log to the base e, because this is our c in this expression. And then over here, this is going to be a very, very, very valuable conversion to convert an exponential into a logarithmic expression to the base e. So a to the n is equal to e to the ln of the base of your exponential times your exponent. So this is going to be a very important one. So you might want to commit that to memory at this point, because when we get into our calculus and exponentials later on, this is going to be really critical for you. All right, so that's just a basic overview of the logarithmic properties. Let's go ahead and use them. In this first example, we have an example of the quotient rule. So this is simply ln of 10 minus ln of 9. We just wanted to expand it. We're not trying to evaluate it. We're just trying to employ the different log rules. So now in this problem, looks like we're going to be using the power rule. So we're going to convert this to a rational exponent, just like we did a couple of steps ago. And this is going to be natural log of 3x plus 2 to the 1/2. Now the power rule states then that this becomes 1/2 ln of 3x plus 2. And we'll move on to this one up here. And this is going to be a combination. So the first thing we're going to do is we're going to use the quotient rule. So this is ln of 6x minus ln of 5. And this is the product rule. So this becomes ln of 6 plus ln of x minus ln of 5. And then for the last one here, we've got a whole boatload going on here. First thing, let's go ahead and break up this quotient. So we have ln of x squared plus 3 squared minus ln of x times the cube root of x squared plus 1. And here we have the power rule, so let's do that one. That's going to be 2 ln of x squared plus 3. This is not the power rule because there's a binomial in here, so this is done at this point. Here we have a product rule. Now you want to be careful about this sign. So this is minus, I want to put everything in parentheses here, ln of x plus ln of the cube root of x squared plus 1. And the last piece inside this parenthesis is going to be this guy. So this is going to be 2 ln x squared plus 3 minus, I'm going to distribute this negative, ln of x minus 1/3 ln x squared plus 1. And there's the expansion. In the next video, we're going to look at logarithmic equations. So I'll talk to you in the next video.